All right, section 7.4 is talking about linear inequalities. So an inequality is a problem that does not involve an equal sign, rather it involves an inequality, a less than, greater than symbol. So we're going to talk about number lines and how to represent these solutions with number lines, how to represent the solutions with notations called interval notation. We're going to talk about the addition property and multiplication property of inequality. Make sure you remember those. And how to solve a linear inequality. And we're going to do a little bit of applications and some three-part inequalities. So a lot of the same steps are involved with solving inequalities that were involved with solving equations, but there's at least one exception to the rules, or one difference in the rules. Okay, so some of the different inequalities that you need to be familiar with are less than, greater than, less than or equal to, greater than or equal to. Now the rule I'll always give you is, as long as the variable is on the left-hand side of the inequality, then you can use the arrows to represent which direction you're going. So for example, again, if you have x and then the less than symbol 3, then if you think about a number line, you know that you're moving in this direction to the left on the number line because the arrow is pointing in that direction. If you have x is greater than 3, then you know you're pointing to the right on your number line. But that only works if x is on the left-hand side of the inequality. So keep that in mind as we're going through this next part. So when solving an inequality, we're finding all the numbers on the number line that are solutions for the problem. So when we're dealing with inequalities, there's not one solution. It is not a conditional equation like we were doing on the previous set of information. We're dealing with inequalities that have multiple solutions to the problem. So for example, when we say that x is greater than 3, that means that all of the solutions greater than 3 are solutions to the problem. So 4 is a solution, 5 is a solution, 3.1 is a solution. So any number that is greater than 3 would be a solution to the problem. So we're talking about an interval of numbers that are solutions. So here are some different ways to represent solutions to problems. So if we have x is greater than 3, some important things to note here. You'll notice that you have a parenthesis at A, and that all of the line is bold to the right. Since it's talking about greater than, we want to shade in the direction that the arrow is pointing. We use the parenthesis because we do not have an equal sign over here. If this problem were greater than, if this problem were greater than equal to, x is greater than or equal to a, then that would change our notation that we would have at the very beginning of this parenthesis here. The second solution that we have is x is between a and b. So again, we have the parenthesis on b, the parenthesis on a, and we've shaded all of the area between a and b. X is less than b, again, the parenthesis at b, and x is shaded in the direction of the arrow, so it's pointing to the left. So we're going to shade everything to the left of b on the number line. Now when we think about our graphs, the first graph is going off to infinity to the right-hand side. So that means that a is the smallest possible value that there could be. This would be a plus 1, a plus 2, a plus 3, all the way up to infinity. So with interval notation, we use parentheses since we're, again, only talking about less than or greater than. We're not talking about equal to. We use parentheses. A is our starting value, and infinity is to the right. Again, the arrow is pointing to the right-hand side, so infinity is on the right-hand side. With interval notation on the second example, a and b are my boundaries, so a and b are the two numbers in the parentheses, and this is telling me that all the numbers between a and b are solutions. On the last one, we're going to the left, which means this number is b minus 1, b minus 2, b minus 3, because we're moving to the left-hand side, all the way to negative infinity. So negative infinity is on the left and b is on the right. So b is the biggest possible value that the solution could be. And actually, I take that back. B is not a solution, but anything less than b is a solution. All right, so when I've changed my problem now, and you'll notice now that I have less than or equal to or greater than or equal to, now my parentheses and my brackets will change. If I have the equal to symbol, then I will be using a square bracket as my endpoint. But you'll notice on the second example that this is just less than, and so I used a parenthesis. So I can mix these symbols. You'll notice I used a bracket with the b because I have the equal to symbol on the b, and I used a parenthesis on the a because I do not have an equal to symbol on the a. So again, the first example, we start at a, we move to the right infinitely because there's no endpoint. So infinity is on the right, a is on the left. We have a square bracket on the a and a parenthesis on infinity. Infinity is always a parenthesis. It will never have a square bracket because it will never ever reach infinity. On the second example, my answer is between a and b. B is a possible solution. So I could substitute B into the problem and it would work. But A is actually not a solution. It's all the numbers greater than A. On the third example, A is a solution to the problem, but B is not. Again, look at the parentheses on B. That tells me it's not a solution. The bracket on A tells me that it is a solution. Now in this example, we're talking about a closed interval here because A and B are both solutions and all the numbers in between are solutions. But again, if you pay close attention, you've got the less than or equal to symbol here, the less than or equal to symbol here. So we have the square brackets on A and B, and the solution is all the numbers between A and B, including A and B. Okay, so write each equation in interval and graph the interval. So x is on the left-hand side. So we're going to graph our number line. We're going to place the number -1 on the number line. Now, I've always wanted to put 0 in there, so here's my -1. This symbol here is just greater than. It does not have the equal to symbol, so we're going to put a parenthesis at 1. And we're going to shade in the direction that the arrow is pointing. So there's my solution. In terms of interval notation, parenthesis, -1, infinity, parenthesis. Okay, now for the second example, you really need to think of this as two different problems. We have the problem x is less than -4, less than or equal to -4, and then you need to sort of reverse this and say x is greater than -2. Notice the direction the arrow is pointing. The arrow is pointing to the -2. The arrow is pointing to the -2. So when we graph this, we have 2 points here. We have 4 and we have -2. On -2, we have a parenthesis because it's not equal to. And on the 4, we have a bracket. And we're going to shade everything in between those two. Now, in terms of my interval notation, parenthesis, -2, 4, square bracket. So a lot of times it will help to do the graph first, and then the interval notation just sort of falls into place from there. All right, so when you're solving a linear inequality, all the steps are the same as when we were solving an equation. So a linear inequality, same rules as equations, can be written in the form of ax plus b is less than c. The less than symbol can be replaced with any of the valid symbols. Just like with equations, I can add something to both sides, and I haven't changed the problem, so I can add c to both sides and the problem hasn't changed. So let's look at this. We have this problem and I want to solve, and then we're going to graph our solution set. So we're going to start by subtracting 2x from both sides. So we end up with 1x plus 4 greater than negative 1. And then we're going to subtract 4 from both sides. So you get 1x is greater than negative 5. And we are technically done at that point. If we graph this, here's negative 5. Because it's just a less than symbol and not an equal to symbol, we do a parenthesis, and we're going to shade to the right because the arrow is pointing to the right. In terms of set builder interval notation, we're going to have negative 5, infinity, and parentheses. Okay, with the multiplication property, things change just slightly. If we multiply or divide by a negative number, then the inequality is going to change the direction. So that's what they're saying here. If I multiply both sides by a positive number, then the inequality is the same. But if I multiply by a negative number, if c is negative, then the inequality is changing directions. So anytime you multiply or divide by a negative number, you will change the direction of the inequality. So here we have a problem. 4x is less than 12, and graph the solution set. So to solve this problem, we want to divide both sides by 4. So the 4 is a positive number. So we end up with x is less than 3. The arrow did not change directions because the number involved, 4, is a positive number. So then we can graph that on the number line, and we can do our interval notation. Okay, so now let me give you an example that tricks sometimes. What if I said 4x is less than negative 12? Well, in order to solve that problem, I'm going to do the same thing. I'm going to divide both sides by 4. Now, this 4 is my c value. Remember how we can multiply both sides by something? So this 4 is c, and this 4 is c. C is positive. So I'm multiplying both sides by a positive number. So the direction of the arrow does not change. The direction of the arrow does not change. It's only when the number that we're multiplying or dividing by is negative that the arrow changes directions. So here's an example of that. In order to solve this problem, I have to divide both sides by negative 2. So 8 divided by negative 2 is negative 4. Oops. And because I divided by a negative number, the arrow is going to change directions. And then again, doing my interval notation and graphing, there's my solution. Okay, so just like before, there's certain steps. The steps really don't change for solving equations except for the multiplying and dividing by negative. We're technically going to get rid of those fractions first. We're going to simplify each side first. And then we're going to combine like terms, get the variable on one side. And in this case, I'm going to tell you that the preference is to get the variable on the left. That's the preference. Try to get the variable on the left. It's going to make things a lot easier in the last step. All right, so we're going to go through our steps here. We're going to get rid of the parentheses, so we're going to distribute to both sides. So we get 6x plus 12 is less than 2x plus 6, and then there's that minus 4 that we have there. We're going to simplify both sides as much as possible. There's nothing on the left to do, nothing to combine together. But on the right-hand side, I need to combine the 6 and the negative 4. And pretend we've got that barrier again, like we talked about earlier. So since I'm not crossing the barrier, I just have to combine those together. Remember what I said. Let's get the variables to the left, because it's going to make things easier in the end. So we're going to subtract 2x from both sides. And then we're going to subtract 12. Now remember, adding and subtracting does not change the direction of the inequality. And then we're going to divide both sides by 4. And remember what we talked about a little bit earlier. The 4 is positive, so it does not change the direction of the arrow. All right, so then we're going to graph that inequality, and we're going to do our set interval notation. So there's our solution with our interval notation. All right, so when we're dealing with word problems, some of the key phrases are, for the symbol for greater than is going to be is more than or is greater than. The less than symbol is less than. Less than or greater than or equal to would be is at least. This is an important one that tend to confuse. Is at least would be the greater than or equal to symbol, and is at most would be the less than or equal to symbol. So Max has test grades 77, 84, and 86. If he wants an average of at least 80 on his 4th test, what are the possible scores he can make on his 4th test? So we're looking for that range of test scores that he could possibly get on the last test to keep at least an 80 average. Okay, so X is going to be his 4th test score. Here's our equation. To find our average, we're going to take the 3 test scores that we know, 77, 84, and 86, plus that test score that we don't know. We're going to add them together and divide by 4. The problem said to keep at least an 80. So here's the symbol that we use for at least. Okay, so a little bit of simplifying here. 77 plus 84 plus 86 is the 247 plus x. Again, we don't like dealing with the fraction, so we're going to multiply both sides by 4 to get rid of that 1/4 or that 4 on the bottom. They cancel out. You're left with the 247x greater than or equal to 320. We're going to subtract the 247. And so we end up with x is greater than or equal to 73. So when we're looking at that, in order for him to get at least an 80 on his exam or his final grade, he must have at least a 73 on his last test. So it's 73 or more to get an 80 on the final test. So if we wanted to graph that, the answer would be x has to be greater than or equal to 73. So if we wanted to graph that on a number line, here's our 73. Because it's an equal to symbol, we can use the square bracket and arrow up. And then in terms of the interval notation, it would be 73, comma. I'm going to put infinity, but that might be debatable to some people. Some people might feel like that number should be 100 because you can't get higher than 100 on a test score. But we'll go ahead and leave it as infinity for right now. Realistically, it's probably supposed to be 100. So if it were 100, let's go one more thing. If it was to be 100 as the highest possible test score, then our answer would look like this with the square bracket on the end because 100 is a possible solution. All right, our last two topics, when we're talking about three-part inequalities, three parts just say that you have numbers that are between other numbers. So 6 is between -2 and 8. In this case, x is between two other numbers. Oops, sorry. X is between one number and another number. We have to make sure when we're doing these problems that these inequalities are pointing in the same direction, or that changes the way we read the problems. So when you solve a two-part or a three-part inequality, you have to treat each part separately. So we're going to take the 2x plus 5 less than or equal to 9, and we're going to solve this part of the problem. And then we're going to get x is less than or equal to 2. And then we're going to have to do the other part of the problem, which is this part. So technically the problem is written like this. And I like to reverse the problem when we start. Look at this carefully. The arrow is pointing to the 2, to the -2, so we need the arrow to point to the -2. Divide both sides by 2. And so here are our two solutions. So notice the way that this is written. The arrows have to point in the same direction. So the arrow is pointing to the number. The arrow is pointing to the x. The arrow is pointing to the x for the 2, and the arrow is pointing to the number. So this is our compound inequality here. When we graph that, here's the -7/2. Here's the 2. The 2 has the equal to symbol, so it's a square bracket. This one has a parenthesis, and our answer is all the numbers in between. All right, I hope this is helping. Keep in touch with me again. Let me know if you're having problems. Have a great week, and I'll talk to you later.